In this video, we are going to talk about section 1.3, infinite series. So first of all, let me recall you the definition of series from high school. So an infinite series can be viewed as a sum of an infinite set of numbers. It has the form a1 plus a2 plus dot 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 plus an plus dot dot dot. So basically, a series is a sum infinite times, right? So now you may have a question that is it possible that we sum infinite times? The answer is yes, we can. So let's look at an example here. So let's suppose that we have a unit square and both sides have length 1. Alright, so let's look at the picture here. So what we have is a unit square. And I know that both sides have length 1. Alright, so the first step, I am going to cut half on this square. So you know that the area of the square is 1, right? Because the area is 1 times 1, which is 1. And then if you cut half, so the area that you cut half here, this is going to be just 1/2, right? And then the next step, I am going to focus on the piece that I have not shaded. And then I cut half again. So I got this area. This area is equal to 1/4, right? Because you just cut half from what we have left. And next step, I am going to focus on what I have from the previous step, and then I cut half again. So I have this area that I shade in green. So the area here is going to be 1/8. So if you keep repeating this thing again and again and again, so what you get, you're gonna get a series. And that series is 1/2 plus 1/4 plus 1/8 plus 1/16 and so on. So you can keep doing it forever and forever, right? Because you can just cut half again, cut half again, cut half again, cut half again. So you get infinite terms, right? And then you can see that eventually at the end you're gonna get that this sum infinite time here is equal to 1, because at the end, once you repeat this process, you're gonna get the total area of the unit square, which is 1. So this is a good example to show you that it is possible to sum infinite times, and it is possible that the answer after you sum infinite time is just a real number. In this case, we're gonna say that a series converges to 1. That is the motivation behind the series. Now we're gonna just look at the formal definition of series. Alright, let's move to the next page. So this is the formal definition of series. So given a sequence an, so if you sum a1, a2, a3 and so on infinite times, so you can use the summation notation here. And this thing is called an infinite series. So in order to find the value of the infinite series, so you can find by looking at the limit of the partial sum. What is the limit of the partial sum? So let's look at what we define here. So we can define S1 to be A1. We can define S2 to be A1 plus A2. We can define S3 to be A1 plus A2 plus A3. And so on. So we define Sn to be the sum from A1 to An, right? And what we need is just the sum of an infinite times. So actually what we need is just the limit of Sn, right, when n go to infinity. So we want to know the value of Sn when n go to infinity, and that thing is going to be the sum of a sub n infinite times. And just Sn here, we're gonna call it partial sum, right? So actually the value of the series is just the limit of the partial sum. So if you have a hard time to follow the definition in this box, so let's look at an example here. So let's suppose that I have an infinite series summation of 1 over 2 to the n from 1 to infinity. So if I just pull out only one term, so I have s1 equal to 1/2. If I add the first two terms, I get 1/2 and 1/4, which is 3 over 4. And then s3, this is going to be 7 over 8, because I add 1/2, 1/4, and 1/8. And then s4, I add 1/16 to the series, and then I get 15 over 16. You can see that the value of Sn just getting close to 1, right? Well, this is the same example as we did on the previous slide. So we cut half first, and then we add a quarter later, and then we just add 1/8, and we just add 1/16, and so on and so on. So at the end, so you should get 1, right? And then you can see that the value that you have here is just 1/2, 3 over 4, 7 over 8, 15 over 16. It's just getting close to 1, right? Now let's look at some forms of series. The first form that we're gonna learn is geometric sums and series. This is the most common one. You have seen this one before in high school, but let me give you a review here. So in a geometric sequence, each term is found by multiplying the previous term by a constant. So the standard form of the geometric sequence is an equal to a times r to the n minus 1. So actually if you expand it, so it's gonna be a, and then ar, and then ar squared, and then ar cubed, and so on. So the factor that you multiply each term, this is called the common ratio, and we use r to denote the common ratio, right? Have you remember this thing from high school? So you're gonna have the first term called a1 or a. This is your first term, and then each time you're gonna multiply your previous term by a common ratio r. That is how geometric sequence work. And then when it's come to series, so you can see that your first term is just a. Your second term is ar, and then when you just looking at s2, which is a partial sum, so it's gonna be a plus ar, and then the partial sum for 3 terms, so you're gonna get a plus ar squared, and so on. So at the end, so you're gonna get Sn to be a plus ar plus dot 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 up to a times r to the n minus 1. And then I call this thing the equation 1. And then after that, I multiply r to the equation 1. So I get r times Sn equal to r times this thing in parentheses. And then after that, I expand my equation. So I get ar plus ar squared plus dot 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 up to ar to the n. I call this thing the second equation. And then after that, I subtract equation 2 from equation 1. So what I have left, I am going to have the one that I highlight in yellow here. Well, you can simplify it by yourself, but this is what we have left. So S sub n this is equal to a times 1 minus r to the n over 1 minus r. This is the same formula that you learned in high school. Same formula that we learn from high school. This is the formula we use to find geometric sum of n terms, right? And then when it's come to series, we're gonna take limit of Sn. So when you take limit of Sn, you can see that the behavior of limit gonna base on the value of r. So if r less than 1, so when you take the limit here, so you get a over 1 minus r. So in this case, we're gonna say that the geometric series is convergent. And if you have absolute r bigger than 1, so you're gonna have that the series is divergent. Well, when you have r equal to 1, so what you have is you're gonna have a plus a plus a plus dot 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 dot. And that means it's go up to infinity. So this is also divergent. When r is equal to negative 1, so what you have is you're gonna have a plus negative a plus a plus negative a plus dot dot dot. So you're gonna get the partial sum that oscillate between 0 and a. So this is also divergent. So the only case that is going to be convergent is the case that absolute r less than 1. So this is the proof. But when you use it, so you can just memorize this thing. So geometric series. So when you face geometric series, so if absolute r less than 1, then the geometric series gonna sum to a over 1 minus r, where a is your first term, right? And then your r here, this is going to be your common ratio. Otherwise, the series is divergent. So if absolute r is not less than 1, so that means the series is divergent. So let's look at example 8 here. Alright, we're gonna get better after we complete this set of examples. So let's start by the first one. So I have summation of 1 over 2 to the n from 1 to infinity. So if I expand the thing, so you can see that I have 1/2 plus a quarter plus 1/8 plus 1/16 plus dot 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 dot. So this is a geometric sequence, right? And then it sum up infinite time. So this is called geometric series. So here we have the first term a equal to 1/2, and we have the common ratio r equal to 1/2. How do I know that r equal to 1/2? Because each term, well, I have to multiply 1/2 to get the next term, right? And from here, observe that absolute value of r is equal to 1/2, which is less than 1. So that means the series is convergent and its limits is a over 1 minus r, which is 1/2 over 1 minus 1/2, which is 1. Right, this is the answer for question A. Alright, let's look at question B. So here you have summation of 2 times e to the negative n when n's go to 0 to infinity. So let's expand this thing. So the first term, when you plug in n equal to 0, so you get 2, right? Because you get 2 times e to the 0, which is 2. And the next term, when you replace n equal to 1, so what you get is you have 2 times e to the negative 1, which is 2 over e. And then the third term, you replace n equal to 2, so you're gonna have 2 over e to the 2, which is 2 over e squared, and plus dot 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 dot, right? Well, here this is the geometric sequence that you have a equal to 2 and your r, which is your common ratio. This is going to be 1 over e, right? Because each term you need to multiply 1 over e to get the next term. Alright, from here you observe that, well, your absolute r is going to be 1 over e. This is also less than 1. So the series is convergent. So this series is convergent and it's converged to the limit, which is a over 1 minus r, and that is 2 over 1 over 1 minus e. If you simplify this thing, so you get 2 over e minus 1 over e, right? And that is 2e over e minus 1. And that is your limit of this series. Does it make sense? This is supposed to be easy content for you, so you just need to simplify and figure out your first term a and your common ratio r, and that's all. Alright, let's look at part C. So part C, I'm gonna just expand this thing again. So before expand, I'm going to just simplify first because it looks messy now. So what I'm gonna do, I'm going to just simplify a little bit. So I have summation of summation n equal to 0 to infinity. So on the top, I am going to pull out 2 from the first term. So I'm gonna get 2 times 2 to n, right? That's the first term. And then, alright, so I just highlight it here so you don't get confused. And then the next thing is I'm going to just move negative 1 to the n, plus 1 to negative 1 to the n, and negative 1. So this is what I just did. So I just split it into 2 pieces, and then on the denominator I have 5 to the n. The reason why I do this because I want to group the thing that raised to the n together. So next I'm going to just change 2 to the 2n to 4 to the n, right? And then I just do negative 1 to the n here, and then negative 1 and over 5 to the n. Alright, now I can just group everything together. So first of all, I'm going to pull out number 2 and negative 1 here. So I pull out those 2, so I have negative 2. Alright, and the remaining terms, I group them up together. So I have negative 4/5 to the n, right? And this thing is going to be negative 2 for the first term, because when I plug in n equal to 0, I get negative 2. And then the second term, I plug in n equal to 1, so I'm gonna get 8 over 5. And then the next term, I plug in n equal to 2, so I have minus 32 over 25 plus dot 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 dot. So here you can see that your first term a is negative 2, and your common ratio r is going to be negative 4 over 5. We can see that our absolute r, this is 4 over 5, which is also less than 1. So the series is convergent, and the series we know that the series is convergent, right? And then it's also goes to the limit a over 1 minus r. So this converge to a over 1 minus r, which is negative 2 over 1 minus 4/5. So after you compute this thing, so this is going to end up with negative 10 over 9. Alright, and that is the answer for this question. So the series is convergent and its limit is negative 10 over 9. Alright, let's move to another example. So example 9. So I want you to evaluate the following geometric series or state that the series diverge. So here this is a geometric series, right? So we have 1 plus 1.99 plus 1.99 square and so on. So here we have a geometric series with a equal to 1. This is the first term, and the common ratio r is 1.99, right? Because each term you multiply 1.99 to get the next term. So since our common ratio r, we take the absolute value and get 1.99. This is not less than 1. This is bigger than 1. So we conclude that the series diverge. Right? So as long as your absolute r is not less than 1, you can conclude that the series is divergent, and that's it, your answer. That's all. Alright, let's look at part B. So here I have the first term a equal to 1. And then I have the common ratio r to be e over pi, right? Because this thing is just, you need to multiply e over pi to get the next term. And e over pi, this is approximately e is 2.71, pi is 3.14, right? And this is for sure less than 1. So because absolute value of r less than 1, so the series is convergent and it's converged to the limit a over 1 minus r, which is 1 over 1 minus e over pi, right? This is the thing that we just figured out before. And then we have pi over pi minus e after you simplify it. Now let's look at example 10. So this is the example. Now let's look at example 10. This is the example that show you how to convert decimal to fraction when you face the repeat decimal. Alright, so we have 1.03535 repeat. So this thing is actually 1.035, 35, 35, 35, and so on. So you can see this is the repeat decimal. So we're gonna use the idea of geometric series to convert it to fraction. So what are we going to do is we are going to simplify this thing again. So this is going to be just 1 plus 0.035 plus 0.00035 plus 0.0000035, right? Plus dot dot dot. This is how we do it. And then you can see that the term that I highlight in yellow here, this is a geometric series, right? So just this part, this is a geometric series that have the first term a equal to 0.035 and the common ratio r to be 0.01, because each term when you move from the previous term to the next term, you can see that you multiply 0.01. And here, since your absolute value of r is 0.01 less than 1, so the series is convergent, right? So, and its limit is a over 1 minus r. All right. So here we come back to our original problem, and we have 1.035 repeat. This is going to be 1 plus this thing is just a over 1 minus r, right? Because the geometric series is convergent, and then you know its limit, and that is 1 plus 0.035 over 1 minus r, which is 0.01. And if you use your calculator or something like that, so you're gonna get 1 plus 0.035 over 0.99, which you can simplify to be 205 over 198. Alright, this is how you convert repeat decimal to fraction. Alright, let's learn the last topic for this section, which is telescoping series. So the idea of telescoping series is that you can cancel out some terms after expanding the series. So I have two examples here to show you that after you expand the series, you can cancel out some term, and what you have left is going to be super easy to figure out the limit of the series. Well, let's look at example. So example 11. So I want you to find the following series. So I mean, evaluate the value of the series. So part A, I want you to find summation from n equal to 1 to infinity of 1 over 3 to the n minus 1 over 3 to the n plus 1. So first, let's expand this thing. So once you expand this thing, you're gonna see that the first term is going to be 1 over 3, right? 1/3, and then minus 1 over 3 square. The second term is going to be 1 over 3 square minus 1 over 3 cube. The third term is going to be 1 3 cube plus 1 over 3 to the fourth power, and so on. Well, you can guess from here that, well, it does look like this term and this term gonna cancel out, right? And this term 1 over 3 cube and 1 over 3 cube here gonna cancel out, and it should keep repeating this pattern and cancel out all of them. So at the end you should have only 1/3 left, and then the series should convergent to 1/3. That is your guess after you expand this thing, right? So we're gonna do this thing by just make it more formally. By what I'm going to do is I'm going to just compute the partial sum Sn first, and then I will take limit when n go to infinity. Alright, so let's consider the partial sum. Let's consider the partial sum Sn. So Sn is going to be summation of 1 over 3 to the k minus 1 over 3 to the k plus 1 k from 1 to n. So I switch my dummy variable from n to k because I want to save my n for a fixed number. So I'm gonna switch my n from the problem to k, just to make different variables so they are not messy. And then after that, well, I can expand this thing, so I have 1/3 minus 1 over 3 cube 3 square, sorry, and then plus 1 over 3 square minus 1 over 3 cube, and so on. And at the end, I'm gonna have 1 over 3 to the n minus 1 over 3 to the n plus 1. So this is after you expand n term, and then you can see that something cancel out, so 1 over 3 cube gonna cancel with something inside the dot here, and then 1 over 3 to the n gonna cancel with something inside the dot here. So at the end you have 1/3 minus 1 over 3 to the n plus 1. So this is the partial sum Sn. And then the value of the series is going to be summation of 1 over 3 to the n minus 1 over 3 to the n plus 1, right? And then we sum from 1 to infinity. So this thing is going to be limit of Sn when n go to infinity. And this is the limit of 1/3 minus 1 over 3 to the n plus 1. So the limit here go to 0. So what you have left is just only 1/3, and that is your answer. Right? You feel better? Alright, so let's do another question. So another question, let's do summation of logarithm of n plus 1 over n from 1 to infinity. So again, I'm gonna compute the partial sum first. Let's compute the partial sum Sn. So I'm gonna have Sn equal to summation of log, well, instead of using n again, so because I'm gonna set n to be my number, fixed number, so I'm gonna switch n to k. Alright, so k from 1 to n, and this is going to be summation k from 1 to n. So use the property of logarithm, so this is going to be log k plus 1 minus log k. Alright, and then after that I expand everything, so I have log 2 minus log 1, right? This is the first term, and then plus log 3 minus log 2, this is the second term, plus dot dot dot, and then the last term must be log n plus 1 minus log n. Alright, and then so something cancel out, so log 2 here gonna cancel with log 2 here, log 3 here gonna cancel with something inside of the dot here, so log n here gonna cancel with something inside here. So think carefully, so you can see that everything cancel out, and what you have left is just negative log 1 plus log n plus 1. And negative log 1, this is 0, right? Because log 1 is 0. And what you have left is just log of n plus 1. So this is the partial sum for this question. And then when you compute the series, so summation of log n plus 1 over n from 1 to infinity. So this is going to be the limit of the partial sum, right? And that is the limit of Sn, and this thing is limit of log n plus 1, right? Because you just use from what you compute before, and this thing is just past infinity, right? Because logarithm just blow up when n go to infinity. So therefore you can conclude that this series log n plus 1 over n, this is divergent. And that's all. Alright, so we're gonna stop here for section 1.3 and see you on the next video.